Hello, you're welcome to my channel. My name is Silo and in this video we're going to deal with related rates problems. So this kind of problems demand one to find the rate at which a particular quantity changes, all right, or the rate at which quantities changes, maybe one after the other. Good. But then you'll be given some quantities and then a rate that relates with the rate which you're asked to find. Good. So it's just all about rate of change anyway. Okay, so these are the steps you can use to solve problems on related rates. So first thing is to draw a diagram to represent the information given, so that you'll be able to know what you're doing. It's very helpful. The next step is to label all the quantities, their measures, and rates of change if given. So all the information given, that's the next thing you do. Okay, the third thing is to think of an equation that relates all those quantities. So you're given a lot of quantities or some information. You just think of an equation that relates all of them. Then the fourth step is to reduce the number of quantities by substitution if possible. Now this first step is very important. Now sometimes most of the quantities involved in the problem are not going to be helpful in finding the solution needed. So you have to try to think of how are these quantities related to each other. Then you make a substitution to reduce the number, like elimination method, right? To reduce the number. Okay, but here we are not talking about system of equations. Anyway, you differentiate both sides of the resulting equation with respect to time. Yeah, this is where the rate comes in. So if you want to know the rate at which a certain thing changes, we use the derivative. The derivative is the instantaneous rate of change. That's the rate at which a quantity changes at an instant, at a particular time, when something is at a particular level. So you want to know the rate at which the other quantity is changing at that moment. So that is why we use the derivative. So this is just an application of a differential calculus. So if you differentiate it with respect to time, let's say you differentiate let's talk about distance covered. Okay, when you differentiate that with respect to time, you'll get the speed at that instant, at the particular position that the person is on the journey, on the course of journey. If you take the derivative, that is the rate at which this position changes with time, that gives us the speed. Anyway, so that's still an application of rate of change. Then the sixth one is that we use the derivative equation, that's the equation we just differentiated, to answer the question given. Okay, so we're going to apply all the steps in doing this example. So let's head right into it. Okay, so for the example, we are given that water is pumped into an inverted cylindrical conical tank. So this right cylindrical conical tank is just a conical tank, gotten from a right cylinder of height 6 feet and has radius of 3 feet at the top. Now this water is pumped in at the rate of 5 cubic feet per minute. What is the rate at which the height of the water level is rising when the water is 2 feet deep? That's when the depth of the water is 2 feet. Good. So you first of all want to draw a diagram, to represent what you're given. So I've already gotten my diagram drawn. Okay. So here we have 5 cubic feet per minute. That is talking about, here we talk about water being pumped in. All right, so if this water is being pumped in at what is given is 5 cubic feet per minute, then the radius at the top is 3 feet, the height is 6 feet. So I'm going to measure from here to here. Sorry, let me use blue for that. The height from here to here is measured as 6 feet. Then this right here, that is the water level, is 2 feet deep. So let's say 2 feet like this. Then this is the water content. So let me do a little thing to show the water inside. Good. Don't want to make the work too dirty. What else is being given that we've not taken note of? Okay, probably nothing. Even if we've missed something, we'll still get back to it. So this is a diagram. Then the next step is to label all the quantities. So you notice what we've been given. We're given that's the radius of the conical tank. Let me use big R to denote that. This is the height of the conical tank. Now look at the way the water is shaped. It has a conical shape. itself. All right, so this has a radius, so I've used little r for the radius. Now this is the level. They say what is the rate at which the height of the water level is rising when the water is 2 feet deep. That's when the depth of the water is 2 feet. So since this is the level of the water, so maybe I can just call it a little h, but it's not it's just a particular h, so I'm just saying h naught. So this is the instant, you know, as this water is being pumped in, the water level is rising. All right, good. So you need to identify what we are asked to find. We're asked to find the rate at which the water level is rising. So let's use the rate, take note of that. So the rate at which it's rising, take note of the derivative with respect to t, that's time, of what? Of the height of the water level. So you want to find the rate at which it is changing. Now by changing, it may be rising or going down. It will depend on the value of the result. So if the result is positive, it means that it's rising. The result is negative, it means that it's falling. That is, it's getting smaller. In other words, water is leaking from the cone. But it's not going to be the case provided we get everything right. Okay, now look at this. I also want you to take note of this. Water is being pumped in at this rate. What does this mean? That the volume of water in this conical tank will be increasing at this rate. Every minute 5 cubic feet, okay, of such will be coming in. That is also the rate. So when you see something like this per minute, it's just like saying over time. So per minute, right? So that tells us about rate as well. So this is the rate at which the volume of the water, so let's use V to denote the volume of the water, is changing. And since it is changing every time the volume of the water changes, so it's not going to be a constant value. In other words, we say it depends on the time. So it is given as 5 cubic feet per minute. Okay, so this is what we are asked to find. Let me put a question mark on it. So this is given as 5 cubic feet per minute. Okay, that's nice. Then what else? We're given the at this instance, that's at a particular time where the water level is 2 feet deep. So I'm just using that to be h naught, where it is 2 feet deep. Now we're given that the height of the conical tank is 6, which we've called h, and then this one is r. Anyway, so this is the question. So we want to find the h dt. All right, that is it. So that's how to label. Then the next thing would be to think of an equation that relates all the quantities. Well, it's not too hard to think of it. Here we are talking about volume of water, and as you can see, this water has a conical shape, okay, because it's inside an inverted cone, a conical tank. So what happens is that since the shape of this water is a cone, like it's conical in shape, and then we are looking at volume. So you just think about the volume formula of finding the volume of a cone. So the volume of a cone is given as 1/3 the surface area, that is a cross-sectional area times the height. Good. So this is just the formula, okay, where this is radius and then that is that. So this is the formula for finding the volume of a cone. So looking at this water, okay, so in our own case, we are going to say that the formula is V of t, where the volume changes as time changes, is now 1/3 pi, okay, those are constants. Then r squared. Well, the radius of the water is also changing. Now when this water level is rising, these are slant lines, so the radius will also increase. It will no longer be small r, it will be more than that. So this small r, just maybe let me just put it down here, small r naught, just the way I'm saying h naught, to show you just that instant. But for any time the radius changes, so I'm going to say r of t, and then I'm going to square that r of t. Then I'm also going to say times h of t. Okay, so that's the formula that will relate all the quantities. Then the next thing is to reduce the number of quantities. That's number 4, which I said was very important. Good, it's still very important anyway. So look at this. We have the radius, we have the height. The question needs us to find the rate at which the height changes, so we don't need the radius, all right? So we try to see how we can reduce the number of quantities in here, in other words, number of variables, to having just the height, since the radius would not be helpful. We don't even have any information about the radius of the water level when the height is 2 feet. That's when the depth is 2 feet. So what do we talk about? What do we do for the radius to eliminate it? Anyway, this is what we can do. We're going to use the fact that if we cut through this conical tank, this is what we're going to see here. It's going to be like this. If you cut through, you're going to have this right here. Let me now use this for that. Let me use blue for that. Okay, so we have that. Then look at the top. We have that. That is the radius of the conical tank. Okay, something like this. Good. And then we have the slant height. That is the conical tank. That's the blue. Then for the water level, okay, if you cut through, you'll see from here to use the radius. So I'm just taking this part. Okay, and then that's it. Now you notice that these two, this now becomes two triangles, the blue triangle and then the green triangle, where this is the complete part of the green triangle. So they is the same thing. I'm just trying to draw it in a different line to show you the green alignment and the blue alignment. Oh, I cannot, so let's just do it. So we have the first triangle with side length 6 feet, because the height of the this thing, the height of the tank is 6 feet. Then we also have the depth of the water, which is 2 feet deep. So from here to here is 2 feet. Good. Then what else do we have? We have the radius. The radius of the water, we say let's use little r to denote that. Then the radius of the this thing is big R, which is 3 feet. Okay, good. Now these two triangles are similar because they share the same angle here. They are both right angle triangles. And then lastly, since the two angles here are the same, these two angles must be the same, because the sum of interior angles of a triangle is 180 degrees. That means that these two triangles are similar, and by similar triangles, the ratio of the corresponding sides are equal. So that means when we take the ratio of the height, that is the depth of the water at the moment, which we call little h. Let me not use 2 for that. Let me use little h for that. You know, we are trying to get something for h of t, not just the particular h naught. All right, so let me use little h for that. Then this is little r. Okay, good. Now look at this. Yeah, so for similar triangles, the ratio of the corresponding sides are equal. In other words, the height of the small triangle divided by the height of the large triangle is the same thing as the radius of the small triangle divided by the radius of the large triangle. So we make cross multiplication, make r the subject, so that we can substitute for r in terms of h. Take note, this I'm looking at this as non-constants. Anyway, that's I'm not looking at the 2 feet depth. So making r the subject, multiply both sides by 3. That means that r is going to be h over, that will be 3h over 6. But 3 cancels itself, 1 goes into 6 2 times. So that is r in terms of h. So we're going to make the substitution. In place of r, we're going to put h over 2. But this r has been squared. We square that. Okay? And then we make the replacement. That means we're going to have v. Well, I'm going to come back to v of t. Let me just use v for now. When we need it, I'll come back to that. Then we have the h right here. Well, we can rewrite this a little bit. That'll be 1 over 3 pi h squared times h. Maybe let me say 2 squared is 4. So maybe let's say 1 over 4. Then h squared times h is h to the 3rd power. So this is v right here. Okay, that's nice, isn't it? Okay, so after getting this and we've reduced the number of equations, let's see what we need to do next. So reduce the number of quantities. The next is to differentiate both sides of the resulting equation with respect to time. So we differentiate the left hand side with respect to time, and this is a variable. It depends on time. So we differentiate this with respect to time, permitting me to use the prime notation. So we differentiate v of t, okay, with respect to t. That means v prime of t. Well, this is pi over 12. All right, we'll multiply this. They're just constant. Then we differentiate h raised to the power of 3 with respect to time. Now take note that h itself is a function of t, and this is the function raised to some power. In other words, we have a power function of a function. So it's a function of a function, which means we're going to make use of the chain rule. So when you differentiate the outside function, which is the power function, that means we're going to have 3, you use the power rule, h, you reduce 3 by 1, that is 2. Sorry, I'm saying 2, I'm writing 3. How? Okay, but since h itself is a function of t, we multiply it by, so let me put the of t here, we multiply it by, that's not nice enough. So this is h of t, Good. We multiply it by the derivative of t, derivative of h of t with respect to t. That is the chain rule. Differentiate the outside function, multiply by the derivative of the inside. Good. So this is h of t. Okay, that's what we've done using the chain rule right there. So the next thing is to reduce this a little bit. That'll be pi over 4. That is 3 over 12 is 4 at the bottom. That this is h squared times h squared of t times h prime. Good. H squared of t times h prime of t. So, but you notice that h prime of t, which is the derivative with respect to t, and then this is v prime of t, that is the derivative with respect to t. So let me rewrite this for you to see. So this is the derivative of the volume, which changes with time, with respect to time, is equals to pi over 4 times this, which is the square of the height as time changes, then the derivative with respect to time of the height. So what are we looking for? We're looking for the derivative with respect to time of the height function. So what if we make this a subject of formula? Are we not done? Good. So to do that, we look at this is given as 5 cubic feet per minute. This right here, we are given at a period, that is, we are given a particular value of 2 feet for the height. So what we have to do is to say when, so this is where I'm going to make a substitution. I say when the height is 2 feet deep. All right. In other words, at h naught. So when it is 2 feet deep, what happens? Well, since this water, water is pumped in at this rate, it's a flat rate. That is all the time. That is the rate. So it's a constant rate of change. This right here is going to be 5 feet deep. Sorry, 5 cubic feet per minute is the same thing as pi over 4. So it's the same thing as pi over 4. Then h squared. But h itself, that is a situation where h is 2. You substitute 2 for h. That is 2 feet. Then you multiply it by what we don't know yet. That's what we're trying to find. That is the derivative. Let me clear this. So you multiply by the derivative with respect to time of h of t. Okay, that's nice, isn't it? So we square this. When you square 2, you have 4. Notice that 4 will cancel out with 4, leaving us with pi. To make this a subject, just divide both sides by, that is the ddt of h of t. Divide both sides by pi. That will be 5 over pi. Good. So this is the rate at which the height of the water is changing. And since this is positive, it means it is rising, and that agrees with the question. So that is 5 over pi. And we're not going to stop here. It's going to be feet per minute. So you take note, it is feet per minute, not cubic feet per minute as the answer, because it is the height that is rising. It's not the volume that is rising, right? Since it's height can be measured, or let's say distance can be measured with a single unit. That is 5 over pi. This positive is not necessary. I only wanted to show that for emphasis. 5 over pi feet per minute. Now you can convert this to decimal. I didn't do the conversion. Just do the conversion, but this is the exact form. When you say 5 over pi in decimal, it's going to give you an approximation. Okay, so you just take the approximate value, but this right here is it. Okay, I hope you enjoyed the video. Please, we're going to do some more examples. This was just more like an introduction, especially trying to give you the solution steps, right? And I had to try to also go slow on the question. You can see the time. I hope you enjoyed the video anyway. Please don't forget to share the video with friends, subscribe to my channel, and we'll continue with other examples.